Einstein viewed gravity as geometry. He had this idea that gravity isn't like the other forces. What it does is it causes the space-time we all exist in to curve. So there's a picture of this with a rubber sheet that you might have seen. A sheet that's initially flat and stretched, you put down a heavy body on it and it develops a dimple. And that dimple, if you take other bodies and release them from rest, they will fall into the hole, just like an apple falls down when you release it from a height. And so the dynamics, the gravitational waves come in if you have two objects on the sheet. They rotate around each other, and that's just like a binary star system with two stars. And as they rotate, they stir the rubber sheet and you get ripples. Now if you think of the rubber sheet as the equivalent of our space-time, those ripples are propagating outwards, and as they're propagating outwards they're getting smaller. Einstein knew these ripples would be very subtle because he thought the sources of these ripples were likely to be very far away. And it's taken a very long time to build a detector which can see these things, but we've now done it. We've got an event which we detected last September. The way the detector works is it uses mirrors which are hanging from wires. So I want you to picture in your mind a laser emitting a beam of light. That beam of light split into two pieces. One goes that way and the other one goes at right angles. They travel 4 kilometers and they bounce off some suspended mirrors and they come back. Now what gravitational waves do is they cause the suspended mirrors to oscillate out of phase with each other. In other words, when this one's going outwards, this one's coming inwards. Those oscillations are an almost unique signature of gravitational waves, and they're detected with light-sensitive photodetectors back close to the laser on the other side of the beam splitter. So what you see on those photodetectors is subtle changes in the intensity of the light as a result of the mirrors being bashed by gravitational waves. Now to make sure we didn't make a mistake, we built 2 of these detectors and put them on opposite sides of the American continent. And what we saw last September is both detectors registered essentially the same signal at once. And this is basically a smoking gun for a gravitational wave emitted, we think, believe it or not, by 2 black holes over 1,000 million light years from us. And when those black holes got sufficiently close together, they were stirring the rubber so hard that even though they're over 1,000 million light years away, we can still detect the ripples with pieces of fused silica suspended from wires in a vacuum on Earth. Now I think that's absolutely incredible, and I'm very, very proud actually that me and my group have been a part of what is a worldwide effort. There are over 80 groups working together to process the data from this experiment. We've been involved in some of that data analysis, in characterising the detectors, in helping to make the detectors work. So the Sheffield group has really been part of all of this, and that's one of the reasons I can talk to you about it today. So I'm very proud to be doing this little explanation, if you like, so that everybody can understand the fantastic, what I think is fantastic news for science.